Hi, we're going to start our second lecture from Focus 8, Topic B. So we're going to talk about atoms that have more electrons than the hydrogenic atoms and ions that we saw in Topic A. So I have to plug this camera in. Takes a minute. And I have to let. Okay, so let me let my cat out too. Okay, Keeks, you can't scream in class. Go ahead. Okay, so many electron atoms. So when we say many electron atoms, all we're saying is anything that has more than one electron. So mentioned this last lecture, the hydrogen atom is the only chemical system that can be solved exactly. Anything else, any molecule, any atom with more than one electron can't be solved exactly, and we have to start thinking about approximations that might be valid. So the important thing, and I want to show you a picture of this, talks about on this first page that the Schrodinger's equation, our Schrodinger's equation gets more complicated. And it gets more complicated in that all the particles are linked together and you can't separate. So we've seen before, like with two-dimensional translational energy, the particle in a 2D box, you can separate the two dimensions from each other, solve them separately, and then the total wave function is a product of those two. Well, you can't do that here, and let me just show you why. So when we talk about Schrodinger's equation for the hydrogen atom, what we need is a kinetic energy term, and so this is the kinetic energy term for the motion of the electron relative to the nucleus. So we've separated out all the motion of the whole atom going through space. Del squared is called the Laplacian, so it's the second derivative with respect to each coordinate. So this would be the coordinate x for the electron, y, and z. And that's our kinetic energy operator. So kinetic energy is always a function of that second derivative. If it's an electron in a hydrogen atom, then it's pretty much just the electron moving when we talk about this kinetic energy, rather than thinking about too much motion of the nucleus relative to the electron. The electron is so small, it's zipping around and the nucleus is staying stationary. So a good approximation is that this reduced mass is just the mass of an electron. And that electron is moving with some kinetic energy. And then that one electron is attracted to the nucleus with Coulomb's potential. And so this is the Coulomb's potential energy. It's a function of the charge on the nucleus, both the integer, so how many protons you have, and then the fundamental charge on the proton and the electron. So proton times electron makes it squared over 4 pi epsilon naught, which is the permittivity of a vacuum. And then the coordinates that it's a function of are just how far is that electron from the nucleus. And we talked in the last chapter or focus on the fact that this can be solved exactly. And the reason it can be solved exactly is that the potential energy only depends on r. So you can rewrite the Laplacian in spherical polar coordinates to be a function of r as well, and you can solve this problem exactly. When you get to the helium atom, now you're going to have kinetic energy for one electron, kinetic energy for the second electron, and that's a negative there. Then you're going to have the attraction of the electron for the nucleus, electron number 1, the attraction of the second electron to the nucleus, but then you have this term here. This is the problem. You have a term for the potential energy, oops, there should be a psi there, has to be multiplied by psi, for the interaction of two electrons. So these were both attractive lowered the energy because a negative and a positive, the electron and the proton interact in a positive way, whereas these are repulsive terms when you have an electron interacting with another electron. But it's this term right here, because you can see immediately, that means the potential energy is no longer just dependent on the distance, because the angle around here that each electron is at, or in the other dimension, will determine the R12 value. So the location of this electron relative to this, it's not just the R1 and R2, it's also a function of what angle. And so long story short, you can no longer split this Hamiltonian Schrodinger equation, which is the Hamiltonian operating on the wave function. You no longer can split that and make it into ordinary differential equations. So what you have is a partial differential equation that's a function of more than one variable, and it's impossible to solve that. So what we're going to do, which is what everybody does, is use the orbital approximation. So the orbital approximation says that we're going to neglect that interaction term, and we're going to assume we can just solve Schrodinger's equation for each electron independent of the other. So what we're going to do is neglect this last term, and then we'll be able to separate this kinetic energy for electron 1 and its potential energy into one part of the equation and solve that for one electron, and do the same thing for the second electron. And that's where we actually come up with this idea that electrons are in orbitals. So what we're going to say equation 3 shows you, or equation 1, is that the wave function, which is truly a function of the coordinates of each and every electron, we're going to separate it and say it's a product of the wave function for one electron times the wave function for the second electron up to how many electrons you have. And what we're going to use for approximations for these wave functions are the orbitals that were the solutions for the hydrogen atom. So S, P, D orbitals, like you've remembered when you look at the periodic table from general chemistry. So this is just then showing us that that allows us to separate the parts and solve them separately. But it's an approximation. That's an important thing to remember. You think about orbitals from Gen Chem and Orgo and you think they're real, but they're not. They're approximations. They're the only way that we can solve the system, but they're approximations. That's a really important thing to be aware of. So when we think about what this means, if we look at helium, we can think about helium as having 2 electrons in a 1s orbital. And then this shows us that then the wave function would be a product of an s orbital with 1 electron times an s orbital with the second electron. When you multiply that out, that illustration shows you what that functional form will look like. If we do the same thing, except we look at an excited state, we can say if we're looking at helium in the excited state of a 2s1, 2 or 1s1, 2s1, then we're going to have 1 electron in a 1s orbital, another one in a 2s orbital. And I've got these wave functions from page 360, that table of the wave functions for the hydrogen atom. I'm going to multiply those by each other, realizing that the 1s electron is closer to the nucleus. So we're going to say it sees an effective nuclear charge of, it should be a 2, yeah, this 2 right here. The second electron in a 2s is further away, and we're going to say that it's shielded by the first electron, so it's only going to see a nuclear charge of a Z of 1. So we're going to put in Z of 2 for the 1s electron, Z of 1 for the 2s electron. And then I'm just going to multiply those by each other and group terms. And unfortunately, I got almost exactly what the book got, except it has the pi and the A0 cubed in the numerator, which I can't see how I could have gone wrong given they're always in the denominator of the wave function. So I'm putting more faith in my answer, which is usually not the case. Adkins is usually pretty good, but I trust that my answer is right based on looking at that math. So by using this orbital approximation, that's where we come up with the idea in Gen Chem that elements have configurations. They have a 1s2, 2s2, 2p3, something like that, depending on which element you're talking about. So you're essentially stating, if I'm using the orbital approximation, which orbitals am I using? So is it a system of helium where it's in the ground state, like here, where both electrons are in a 1s, or is it an excited state? Is it a different element? So at the bottom, it asks us the question, why don't we just put all of the electrons in the 1s orbital? So why doesn't everything just have a 1s10 for the 10th element, or a 1s12? And the reason it doesn't is because of this concept called spin. Spin makes it so that you can't put more than 2 electrons in the same orbital. So spin is one of those quantum mechanical things, actually comes from relativity. So it's a physical property, much like mass or charge. You can't change it. And you often think of it as a particle is actually spinning on some axis, but that's just a way to visualize it. But apparently that's not really what physicists understand spin to be for an electron or any of the other particles that have spin. So for our practical purposes, these 2 points right here are important. Electron spin is described by a spin quantum number s, and it's similar to the orbital angular momentum quantum number L. It has a fixed value, it's positive, and it's 1/2 for all electrons at all times. Electrons don't have a different spin value. It's an intrinsic property, just like electrons have a mass and a charge. That's a fundamental property of them. Number 2, the spin can be clockwise or counterclockwise, and these 2 states are distinguished by the spin magnetic quantum number. So it's very similar to the m sub L in an orbital. Talks about the projection of the spin on some arbitrary axis. So is it spinning this way or is it spinning the other way? And so the spin creates a magnetic moment because moving electric charge creates a magnetic field. And so you can detect it. So we are always going to, right here, talk about when it has a projection of +1/2 on that arbitrary axis, m sub s of +1/2, we'll call it an alpha spin. And if it's -1/2, we'll call it a beta spin. And those are just arbitrary choices because we don't even have a set axis that we're talking about. But the little discussion below this talks about how spin was discovered. So the silver atom has 1 unpaired electron. So when 2 electrons are paired, then the magnetic moment goes to 0. So a spin up and a spin down essentially add together to give 0 magnetic moment. But if you look at silver, which were the atoms used in the Stern-Gerlach experiments, they showed 2 different magnetic moments about one axis. They didn't show an infinite possibility, so you didn't have a projection of some continuous amount. It was either spin this way or spin this way. And that's that quantized idea of space, essentially, that particles have quantized spins, meaning they're either spinning around the axis this way or counterclockwise, and no halfway in between. But because silver has that 1 unpaired electron, it would always split, and you'd always see within a magnetic field that some particles were deflected up and some down, so whether they're attracted or repelled by that magnet. So because of that 1 unpaired spin, those experiments showed that property of spin, showed that it's quantized, and you either have +1/2 or -1/2. This self-test just takes us back to what we did in focus 7. So in focus 7, everywhere where you see an L, you're going to put in an S. So if our spin is 1, which is what this problem says, this self-test, if we look on page 344, the equation says that then the angular momentum is L times L plus 1 to the 1/2 h bar. But because we're talking about intrinsic spin, it's going to be S times S plus 1 to the 1/2. So 1 plus 1 is 2 times 1, 1/2 gives us a total angular momentum as a result of that electron spin of 2 to the 1/2 times h bar. So a lot of these concepts you should remember from Chem 107. So what I put in square brackets here when we talk about Pauli's principle really shows us when orbitals are full. So how many electrons can occupy the same wave function, essentially. So Pauli's principle says that no more than 2 electrons can occupy any given orbital. And if 2 electrons do occupy one orbital, then their spins must be paired. So you remember that from 107. You can have an electron in a p orbital, and as soon as you put a second electron in there, if one was plus 1/2, the second one has to have a minus 1/2 spin. So as soon as you do that, that intrinsic magnetic moment cancels and it's no longer measurable. Penetration and shielding. So these are concepts you remember. This is talking about why when we look at the orbitals in anything with more than one electron. So in hydrogen, if we were in n equals 2, the s orbital had equal energy to the 3 p orbitals. But that's no longer going to be the case here. So we know that when you get beyond hydrogen, the s's are lower in energy than the p's, and they're lower in energy than the d's, and they're lower in energy than the f. And you should read through this, but it has to do with the effective nuclear charge. And then back in so I just want to find the page that gives you the equation that they're referencing in all this discussion. Yeah, so on page, back in the last focus, on page 261, there's equation number 6 that talks about the average distance. So if you measure the location of electron over and over, what would be the average value for R that you would find? And it's a function of L. It actually gets smaller as L gets bigger because this L term is being subtracted. So that means p orbitals you'll find on average closer to the nucleus than s orbitals, etc. So that's just an important concept. Now I feel like it's very easy to get your papers all mixed up. I apologize. Yeah, so here I'm back. So this discussion uses that equation essentially to explain why the orbitals have the energies that they do. So in this picture, it's showing you that an electron in an s orbital, here is a 2s orbital, is more likely to be found close to the nucleus than an electron in a p orbital of the same shell. Hence, it's experiencing less shielding and more tightly bound. So that's the discussion and the information you need as you read through that. So the next concept, which we're very familiar with, is this building up principle, that we fill the orbitals in order of lowest energy, knowing that each orbital can only be occupied by 2 electrons. So it asks us what's the ground state electron configuration of magnesium, and I didn't do that problem, but you should do that. Remind yourself that you haven't forgotten that concept from Chem 107. Electrons occupy different orbitals of a given subshell before doubly occupying any one of them. So that was always incorporated into Hund's rule in Gen Chem. That would mean if you have 3 p orbitals, each of the same energy, and you needed to put 3 electrons in there, you'd put 1 in each orbital first, and then you'd pair them up. And Hund's rule says that when you put 1 in each, they could have any spin, but the lowest energy state is to give them all the same spin quantum number, so that all either be spin up, alpha, or spin down. And we remember that as Hund's rule. And it gives you an explanation of that here, which makes a lot of sense. If 2 electrons with the same spin can't occupy the same region of space, if you put them in separate orbitals and you give them the same spin, that helps force them to stay apart because they don't want to come together if they have the same spin, because that's quantum mechanically forbidden. So the occupation of d orbitals, I think you can read through that really easily. Hund's rule, there are 5 orbitals, so knowing when they're full. I don't think there'll be any surprises in there, but you can ask me questions if you run into anything. And when we remember how we make cations and anions, so remember this whole thing is based on an orbital approximation. Electrons are in orbitals. So when we make cations, we take electrons off. When we make anions, we add them. When we're in the transition metals, turns out that even though it filled a 4s2 3d9, so this is self-test 8b.4. If we want to know the electron configuration of Cu2+, if the ground state is a 4s2 3d5 or 3d9, probably, because it's one of the coin metals, is actually a 3d10 to fill the shell. However you think of it, when you make the +2 cation, you're going to take it out of the S first and then move into taking them out of the Ds. So that leaves us with a argon 3d9. And when you make sulfur into sulfide, you add 2 electrons, so you're going to fill the p shell, and that will be equivalent to saying you made an argon electron configuration. So it's a huge approximation to say that that term for electrons interacting with each other is insignificant. And so when we make the orbital approximation, qualitatively, it works very well, but quantitatively, if you wanted the actual energies of the orbitals, you would have a very, very, very bad fit. So what we do is use this concept of a self-consistent field. So what that means is if you have something like, let's say we have lithium, and lithium has 3 electrons. So what we're going to do is put all 3 electrons into their orbitals. So it would be a 1s2, 2s1. So use those functions for those orbitals. And then one at a time, take an electron, for example, the 2s1 electron, take the average potential energy that it would see if 2 electrons were in the s orbital, and resolve for its energy. Then hold that guy's function constant as you do the same thing by isolating another electron, looking at it in the field of the other 2 electrons. You go through that process over and over until the energy and the functional forms of the orbitals stop changing. And then you say you have self-consistent field orbitals. So approximation for that, you'll often see it as SCF, self-consistent field orbitals. And Hartree-Fock was the first to do it, Hartree and Fock, so it's usually the HF-SCF method. And the nice thing about this is that when you do that, you see the same periodic trends. So you see shells of 2 electrons, and then S and P 8 electrons, and then you get the D electrons. So you see that same qualitative structure, which just confirms that our idea of the orbital approximation as we look at the periodic table is very valid. But if you want real energies and real wave function properties, how they span space, you have to go through this process and alter the wave functions a little bit. You'll still get the same thing on n equals 1 shell and n equals 2 shell. You get s orbitals, s and p orbitals. They'll have slightly different energy than if you hadn't gone through the SCF calculation, but qualitatively, it's a very valid approximation. So that is it for topic B. We have a couple more topics